We can.
Okay, cool.
All right, next we have Dr. Farhan Hasan to tell us about the slime mold cosmic web.
Thank you. Yeah, great to be back in Santa Cruz. And for those of you who don't know me, I'm Farhan. As Joe mentioned, I just finished my PhD at UCSC, and I'll be headed to Space Telescope for my postdoc. I'll be talking about the slime mold cosmic web and how it affects galaxies. Okay, so we've heard a lot about the cosmic web. I think you all know it's huge. There are structures apparent on super megaparticle scales, including filaments. Deep inside of the cosmic web are dark matter halos, at the centers of which galaxies form. And deep in galactic centers, you have processes like star formation and black hole accretion, which themselves are things that happen on very, very small scale. So clearly, there's a huge range of spatial scales, right? Many orders of magnitude between galaxies and the cosmic web. So it's only natural to wonder what the connection is between the cosmic web and the phenomena of galaxy formation, such as star formation and angular momentum acquisition, things like that, frequency at much smaller scales. Okay, so to understand this connection, you have to first properly identify the cosmic web. And as we've already heard so far, the industry standard for doing this is a tool called DISPERSE, which stands for discrete, persistent structure, extractor, and there are 3 different steps to this. And by the way, most of this talk will be based on the lecture's TNG cosmological simulations, although I do some observations at the very end. So first step to disperse is simply to input tracers in the cosmic web. So typically, and what we use in this work is locations of galaxies for that, so represented by red dots, and specifically galaxies above 8 in stellar mass. This leads to step two, which is where disperse estimates cosmic density fields based on these input tracers, and it uses this technique, as Joanna mentioned, called Delaunay tessellation field estimate. This is just a way to segment space into pyramids, or into pyramids being the galaxy locations. And using this density field, disperse identifies the cosmic web skeleton, spines of filaments. And you can see the filament spines, the black curves in the figure. The main parameter going into this is persistence, which is a measure of how robust the structure, an identified structure is to underlying shot noise and data. You can think of this as like a signal to noise ratio for identifying filaments. But the approach that our group has been adopting is slightly different. So this is where the slime mold, right? This is taking inspiration from right here on Earth, and it is known that these unicellular organisms called slime mold can mold itself into interesting and complex patterns that resemble the cosmic web. And some researchers several years ago, right here in Santa Cruz, were inspired by this resemblance, and they developed the Monte Carlo Fresnel machine, MCPM algorithm, which basically mimics the growth of the slime mold, and in doing so estimates the cosmic density field in a continuous sort of way from the same input tracers, which are locations of galaxies. And basically what it does is, what it has is these agents, virtual agents, which navigate towards sources of food, which is locations of galaxies, and this way it mimics the growth of the slime mold. And from that, you get continuous density field of the cosmic web. And this is an example Stone Digital Sky Survey at Redshift several years ago, where you can see the slime mold estimated cosmic density field of small parallel galaxies. So recently, we applied this model to estimate the cosmic density field in TNG simulation. We've done this for TNG 100 and very recently for TNG 50 as well. And these are slime mold estimated MCPM density fields at different redshift snapshots. Right? Using these, we sort of take an alternative approach to disperse to identify filaments. Right? And what I mean by that is we do something different in step 2. We replace the DTFE density field, which is prepackaged disperse, with the MCPM density field. And as Joanna already showed, I think you can see the visual resemblance with this density field with the dark matter. It's you know, it's a lot more continuous. It's not discrete like the DTFE density field. And from that, we tell customers to identify cosmic web filamentary structure. So what do the structures look like? That's what it looks like. So this is a side-by-side comparison of KG1. We have a slice and KG100 at redshift 0. The dark matter over density is the underlying blue color bar. What's different are the filaments identified from the two density fields. Right on the left, you have the classic DTFE-based filaments. On the right, you have the MCTM filaments, and these are color-coded by the persistence, so how robust they are. So you can think of this as like more yellow means more sort of prominent filaments, more red means sort of less prominent filaments. You can see that despite the same input tracers in the galaxies, there is quite a significant difference in the identified filamentary structure, particularly with the MCTM method. We can identify less prominent filaments, such as this one, nevertheless trace kind of overdense cosmic regions that the DTFE-based method misses. And this actually has a huge effect on what we find to be the connection between the filaments and galaxies, right? So, typically what people do when they study the connection between filaments and galaxies is they measure the distance, the transverse distance of a galaxy to the nearest filament spine. And when we do this, we see that most galaxies actually live very close to MCTM filaments on average, compared to DTFE filaments, relative to which most galaxies, a lot of galaxies live very far from. So distance in this context is actually not a very good quantifier of cosmic web environment. That it's not really going to tell you a lot about what's going on physically. So we adopt a different approach. We estimate what we call the filament line density, right? So it's a 1D measure. Basically, you're considering the filament segment that's closest to a galaxy, and you're summing up the MCTM over density along that segment, and you divide by the length of the segment, as you mentioned, per length, and then can correlate. We can study galaxy properties as a function of this filament line density. So that's what this figure is. This is the median of the specific star formation rate as a function of this filament line density, with line density increasing to your left at different redshift snapshots. So the colors indicate different redshifts. So dark blue is 0, all the way up to brown showing 4. And what you can see, and this is for low mass ring galaxies, what you can see is that there's a clear correlation at low redshift. Same thing for these higher mass galaxies, so intermediate masses, higher masses, and pretty much the same story is seen everywhere, which is that there are these two regimes, right? Or these two epochs. At low redshift, below 1 or so, there's more quenching in galaxies residing in high line density filaments. So this effect starts to decline with time, such that above redshift 1, you see no correlation between star formation and filament line density. A compatible picture emerges when we look at the bound gas fractions. This is the mass of gas bound to a galaxy divided by that mass of the stellar mass. And again, you see that at low redshift, there's less gas in high line density galaxies in high line density filaments, which results in less star formation. But at high redshift, there is pretty much no correlation. We also try to distinguish the effect of mass from filament line density. So these plots over here show the line density on the y-axis, mass on the x-axis, colored by the quench fraction. So redder is more quenched galaxies, bluer is more star-forming galaxies. You can see that at low masses, below 10.5, galaxies quench at progressively higher line density, and so there is a filament effect. But above 10.5, quenching is independent of line density. In other words, this quenching of massive galaxies is an internal effect. And this is not driven by centrals, which pretty much only quench at high masses, but rather by satellites, which are extremely susceptible to the effect of filament line density. And a quick note, when this effect persists, even when we look at even we remove all galaxies within 3 virial radii of the most massive halos at a given redshift, right? The correlations are diminished, but there's still more quenching in high line density filaments at low redshift, and there's still less gaps high line density filaments at low redshift. Okay, and then finally, in the final couple minutes, I'll show you some very recent work I've been doing in TNG 50 now, right? So I have filaments in TNG 50 as well, so it's high resolution, kind of lower volume. So we're digging more into kind of angular momentum related statistics, shapes, stuff like that. So here I'm going to show you the angle of between the spin axis of a galaxy and the axis of the nearest filament segment. And these here are the normalized histograms for this angle, measured in cosine theta. So 1 means the filament or the galaxy stellar spin, measured within 2 times the half mass stellar radius, is parallel to the nearest filament, and 0 means it's not parallel, or it's perpendicular. So at redshift 4, you see that there is an alignment signal. Stars are parallel to the filament. At lower redshift, there is no such signal. It doesn't matter if you're doesn't matter how you're dividing it or what shape. There is no such signal. However, when we look at the dark matter component, right, within twice the half mass radius of dark matter, now you see a signal that persists down to low redshift, right? You see that galaxies with prolate halos and spheroidal halos have their spins aligned with dark matter, or with the filament down to very low redshift. Okay, so I will leave a summary of my talk here on the left and advertise that we're actually applying this method to observations, to a HC archival program that I'm leading. Basically, the idea is to apply this to SVSS, which is what we're doing, to identify filament at redshift 0.5, and then we would probe the gas of the filament using background HC radar spectrum.
Thank you. Questions?
Thank you. So that's very, very interesting work. There's something I worry a little bit about is that when you use DTFE in practice, there are different parameters that we choose. We smooth beforehand, and then we choose a persistence threshold. This is not just persistence threshold based, and then we also prune filaments based on things that would relate to what you call line density, for instance. If it's not resolved by enough density, we just discard the filament. And what you do when you use slime mold is that essentially you go more multi-scale because you recover small scale. So all this consideration of galaxies are closer to filaments now. It might be mostly because suddenly you're zooming in, you're increasing smaller scales, and if you wanted to do that with DTFE, you would have selected a smaller box, smooth less, etc. So I think it makes the conversation about scale even more complex, and so when using slime mold, it is even more important than before that you design metrics to bin filaments in different scales, for instance, because you're even more mixed than when we smooth using DTFE, etc. So, like, have you used different? Like, have you used the mass at the nodes, for instance, to try to make the distinction between different types of filaments? And does it affect your results?
Yeah, so I mean that's a very important point you raised. What we do is we actually smooth the density field that goes into dispersion in the first place. We smooth it on the same scale for DTFE and for MCPM. The scale is like half the magnitude. So there's no and in the paper show the length distribution of the filament too. And we show that we don't actually find those like small scale, what's called streams or something. We don't actually find that when we smooth out the density field in the first place, and then run the square sum. So I think there's we've got to have that step. But it is complicated. It's complicated. There's not like a perfect solution.
Thank you.
Okay, one final question before our coffee break.
Thank you. Fangzhou Jiang from Peking University. I have a similar question slash comment compared to Charlotte's. So there are many ways that you can use disperse, not only in the using tracers of galaxies above certain mass, but also you can pixelize the density field and feed the phase image directly to disperse.
Right.
And there are multiple parameters you can play with, like smoothing, how many times you smooth, with the smoothing spatial scale. What is, say, if you conserve your number density of tracers across redshifts, for example, the persistence ratio, etc. So I tend to like pose this question to the discussion in the afternoon, if it's going to happen at all. What would be so slime mode is another great black box, a gray box. Disperse is the standard gray box. What is the optimal definition of filaments? Like if you want to study filaments connecting dwarfs, what's the point of using like 0.5 megaparsec smoothing length, right? And to me, filaments is like the structures that feeding the growth of galaxies. So at each snapshot across the history of the universe, it is the halos that define what kind of filaments that you should focus on. It's the press sector mass. You need to go perhaps 1 order of magnitude in mass below the press sector mass in order to properly define all the filaments. So this is more of a question than thinking out loud than.
No, you're absolutely right. Like, I think this is a conversation with several of my collaborators, and I don't think I have a very satisfactory answer of what is a filament. But I think it does depend on the scientific problem you're trying to address. Right. So like I prefaced at the beginning, I'm very interested in how really kind of large scale affect smaller scale galaxies. Those who are working on like very kind of small streams coming out of larger filaments, things like that. For them, this would be more of a for them smoothing on 0.5 micrometer scale. So I think it depends on what the scientific problem is.
Thanks, Farhan. Okay, so we are on our coffee break now. Everyone please return at 3:45. And it sounds like Colin might have something to say here.
Well, just remember, we're doing the conference photo before the rest of the coffee break. So if you make your way to the stairs before grabbing food and drink, that would be helpful.